Welcome back. I hope you appreciated this light lunch and that you have enough caffeine in your body to be able to fight off sleep. Just one comment. As 𝐲𝐻P, there are several courses on cathodic protection available according to the ISO standard. According to this standard, there are 4+1 certification levels. And these levels are specific to the application sector, that is, the earth sector, so underground pipelines, then the sea sector, everything that is offshore, and then there is an internal cathodic protection sector, that is tanks and similar elements. Anything that requires cathodic protection from inside, like ballast tanks. And there's another sector, very important in my opinion, that is not very well known in our sector. That is cathodic protection of reinforced concrete. So in order to cover all aspects, we decided to invite one of the associations that in Italy deals with cathodic protection in reinforced concretes. So now the floor to Stefano Ambrosi by Matteo, who will talk about cathodic protection of reinforced concrete. Good afternoon. The topic of my presentation refers to cathodic protection applied to reinforced concrete. This is a way of applying cathodic protection in a different way. We all know that reinforced concrete structure can be subject to corrosion due to chlorides and carbonation. This is quite clear to anyone who takes a stroll in a city. You see many examples of exposed reinforcements. If you walk here along the beach and you turn and look at the buildings, you will see examples of this kind. Of course, you can intervene in these cases with a traditional approach, or you can use something that is a bit more innovative. We've introduced this system about 10 years ago, a system that avoids corrosion in a preventative way, or to stop corrosion when you have to intervene on existing structures. The principle is a well-known one, based on the galvanic cell. When applied to concrete, the cathode will be the reinforcements that we want to protect. The zinc anodes will be introduced in the concrete or outside the concrete. We will see different examples. And the electrolyte is concrete itself. There is an ISO standard for this specific protection system. That's the 12696. So we developed two types of anodes. The first one is based on internal anodes, zinc anodes. The blue one is a protective cover that is applied on the anode. And each anode has these terminal elements. They are installed inside the concrete structure. They are applied directly on the reinforcement metal bars. And then concrete is poured on them to spread all around the anode. The installation is very simple. It does not require any kind of specialized skill. As you see here, you simply have to fold the terminal parts of the anodes on the reinforcement bars, and then you use a metal thread to make sure that the anode remains in position. There is also another type of anode that we developed. These are external anodes that are applied externally on the surface, on the concrete surface. They are zinc sheets. Here, the one that you see here is 250 microns. On the back of the sheet, we have a gel, conducive gel, and it's a self-adhesive system. The sheet is self-adhesive. It can be applied very easily on the surface of the concrete element. And then you can have some mechanical fixing elements to guarantee better stability of the system and electrical continuity. So also in this case, the installation system is very easy and very quick. In this case, of course, you will need to electrically connect the zinc sheet with the reinforced element. In this case, you need to create an electrical connection. Very easy. It can be done in two different ways. The first one by using electrical cables that are fixed to the reinforcement bars before applying concrete. And then, once the concrete element has been repaired, you make the connection with the metal sheet. Another alternative is to use a threaded bar welded to the reinforcement bars. These are both very good systems. Here you see the external appearance of the connections between anode and cathode. As I have already said, this system can be used as a cathodic protection system. You can use it on a system that is already degrading, something that maybe it's a bit old and has been subject to chloride and other problems. And I use this system to stop the corrosion process. This way I can increase the shelf life of that structure. We know that steel used for reinforcement bars in an alkaline environment will be protected from corrosion, but with time, this alkaline environment may disappear. So by using this precautionary system, I can avoid the formation of corrosion in the future. In this way, I increase the shelf life of the structure, especially for those structures that need to be functioning for a very long time or when the environment is very aggressive. These systems don't have to be applied throughout the structure. If I have a viaduct, for example, I don't need to protect the whole structure. I can identify the more exposed elements like joints or the lower part of the pylons. So this way I can protect only those areas that are more susceptible to corrosions. What are the advantages of this system? Well, first of all, easy installation, does not require any kind of cabling. No source of external current, easy and rapid. Does not require any maintenance. I can forget about it. But I can monitor the system to make sure that it's working. And it is a reliable system. We have already obtained data from several installations along the years. This system has to be adapted to the size. We have created a calculation software for the typical structural engineer, someone who's required to protect or restore a concrete structure, and that needs to have the system in the right size, knowing, for example, how many anodes are required. So, depending on a series of parameters, it's a new structure or an old one. If it's a new one, what is the exposure class for this structure? In this case, we can collect several pieces of information, so we can understand what's the amount of chlorides in the environment, what is the average temperature, the duration for this protection system. On the basis of these, based on these parameters, the program provides you with the number of anodes and the spacing between them to be able to protect the structure. The number of anodes and the amount depends also on the reinforcement that's present in the structure. Here you see, in the previous example, we had a continuity of sheets. If the density of the reinforced elements is lower, then you can place the sheets with some spacing between them. In this case, generally, you need to use one or at least two electrical connections per sheet, so that you have a better guarantee of connection between anode and cathode. As I already mentioned, the system can be monitored according to the ISO 12696 standard. There are two possibilities for measuring. You assess the potential drop, taking out the instant off value. This is a measurement that was done a few years ago in Spain. And here you can see that in a few hours, 3 hours, you are able to reach the value that the standard requires. If I want to monitor the system, of course, I have to include several points when installing the system. For example, I need to have a reference electrode to measure potential, and in case of external anodes, I shouldn't connect the anodes to the metal reinforcement directly. Otherwise, I will never be able to switch off the system. So I will need to identify an area of the structure where I can connect the anode and cathode externally, so that I can open the circuit and measure the depolarization. It's a very easy system. We also created a box that allows you to measure circulating current right there, and you can check and monitor periodically the system that you're using. Let's see two case histories. The first one is for the Viadotto dei Parchi. Is the viaduct that was created in Milan 5-6 years ago. Here you see that the right part is the older part of the structure, built around 1970. On the left, we have the second part that was built later on. So the older part is clearly more degraded. There is an water infiltration in the joints. We mapped the potential. This is an operation that we don't do directly. We use the external partners to do this. But you see the black line, that is the joint between the two parts of the viaduct. The external part on the right and on the left is the older part that I showed you before. where we have a corrosion area and the degraded part that is far bigger than the other part. Based on this, we decided how to restore these joints. We, of course, provide mortar for restoration activities of the degraded joints. And we also provided the cathodic protection system suitably sized. And the customer decided to protect an area of about 2 meters on the right and on the left of the joint by using the external zinc sheet. Here you see some pictures of the work. You remember I suggested that you should mechanically fix the sheet because we know that the viaduct can be subject to vibration because of the vehicles that use it. So the mechanical fixing element is very important. You should also seal the sheet's perimeter because the back of the sheet has a gel that allows adherence of the sheet, but it's a water-soluble gel, so you need to seal the perimeter of the sheet to avoid water infiltration. Here you see the joint after applying the cathodic protection system. In white, you see the mechanic and plastic elements. And you can also see how easy it is to install this metal sheet. Also in the areas where the surface is not totally smooth, there are some corners or modifications, the sheet can adapt very easily to the shapes of the structure. Once it's sealed, the sheet can be left visible. It's now probably aesthetically the best solution. So then you can coat the metal sheet with cement products that will increase the protection of the structure because these membranes are water proof and chloride proof. So this way we hide the protection system and we protect the structure. You may think that zinc will consume, so in 10 years everything will be done. No, zinc of course is consumed, but there is a thin layer of oxidation products, so there's no detachment and no problem. Here, in this case, the customer decided to apply the cover only near the joints, and so aesthetically it's not the best possible solution, but it was not our choice. Another example of a work we did in Spain a couple of years ago. This is a different kind of structure. It's an artificial reservoir. It's a pilot project. The authority managing this part of the road, they decided to apply cathodic protection on Pier A and Pier B and to monitor it in time. So once a year, we go there with the customer. We test polarization. We prepare a report where we state that the system was correctly installed at the time of installation and keeps working. Here you see some images of the structure before our cathodic protection action. Here you see its potential mapping, corrosion potential mapping, to identify the areas that are more exposed to corrosion. Here you see other situations in which we applied some fixing elements. Here you see a detail where we applied a sealing product. This is a graph that refers to this structure. In this case, we measure depolarization to make sure that we reach the parameters required by the standard. We've been going there for 2 years. Everything is working perfectly, and we have planned the next assessment at the beginning of 2025. I think this is all for me. I hope it's been interesting enough for all of you. Thank you.
Grazie a lei per la presentazione.
Thank you very much for your presentation. It was really very interesting. Actually, I have a couple of questions popping up. First of all, I'd like to know what type of reference electrodes that you use, whether you use copper sulfate, how you use it, or if you use other materials as well. The reference electrode is silver and silver chloride. We've always used them, and so far, even after some years from their application, they've never showed any damage. So manganese, well, actually for the internal ones, silver and silver chloride. For the potential mapping, for the ones outside, for them we use copper and copper sulfate. The other question refers to the structure. In other words, I wouldn't like that people believe that if we do cathodic protection, something gets adjusted. We do not repair what's already broken. Another aspect to point out is that based on my experience with concrete, I've always had this nightmare of electrical continuity. On a new structure, to do cathodic protection, even if you have a very high current volumes, the possibility of having an intrinsic interference between the protected and non-protected parts inside the structure was a problematic issue. So do you have any guarantee on this? Do you have any method to verify the electrical continuity? To answer your first question, yes, if I act on the structure, on a structure which, due to corrosion, I've lost millimeters or microns of steel, that doesn't mean that if I install the system, I am not going to recover anything structurally. What I do with cathodic protection is just to block the corrosion. So actually, with cathodic protection, I can only stop the rust, or I may decide basically to do some repair works. As for the continuity, that's fundamental. So far, we have not used special methods, but on site, we carry out continuity measurements with a simple traditional tester. Normally, if you have longitudinal bars, especially if you apply them on the outer part, we've normally found sufficient electrical continuity, especially when it comes to longitudinal bars. They are continuous per se. So far, we've always had good results in terms of electrical continuity. Any other questions? Oftentimes, one talks about technology, but never talks about costs. How much would such an intervention cost? Actually, this kind of intervention costs more than a traditional action. It's difficult to quantify it because I can decide where to position it. I may, for example, identify the areas in the structure which are more subject to corrosion and install this only in those areas. Compared to a traditional intervention, we may have a cost that may be twice as much, more or less. So in that viaduct in Milan, 2 meters, 2 meters to the right and to the left of the joint. Yes, the traditional solution, with the traditional solution, I use the passivating product, and then typically that's left see visible. Does this have a cost per square meter? Yes, it has a square. Much depends on the anodes that you apply. The cost depends on the number of anodes. If you apply 4 anodes per square meter, it will cost more. If you apply 2 or 3, that will be different. And also the blades. I mean, if you cover the surface entirely, that costs more. Normally, it's 80, 120 euros per square meter, just to give you a general indication. So thank you very much. for your interesting presentation. Now, as I have announced that this afternoon we're going to have very curious presentations. We have yet another interesting one, Lorenzo Spisni, gas distribution, how to measure efficacy in cathodic protection. Thank you. Good afternoon. Mine is a very difficult task. I have to keep you awake after lunch. I think my presentation is definitely going to be very interesting and very curious. At the same time, I would like to share with you an idea. I will try and prepare a pathway. During this pathway, I will also have the chance, if you wish to participate with me, I will, involve you directly. You will be asked to take a survey, so we can immediately check if you fall asleep or not. Actually, we are trying to describe how we can measure the effectiveness of cathodic protection. I've played a bit with artificial intelligence, as my other colleagues have done. And artificial intelligence is telling us, is giving us a couple of information. Artificial intelligence is also providing us interesting opportunities to choose certain methods. So we will choose a method. We will play a bit with parts of assets. So material that has been damaged, some parts more, some parts less. And then we will introduce the case study, which is quite peculiar. In this presentation, nothing should be taken for granted. So when I ask you for your help later on, the idea is that actually I'm going to show you something quite peculiar. And then we will talk about a reality in which there are interferences, non-stationary interferences. There's also the possibility to mitigate them, and everything has already been regulated. In other words, if you take Lazzari's book, everything I'm going to talk about has already been discussed. Yesterday evening, somebody told me actually there's nobody presenting a case of a corrosion, the case of a corroded tube. And actually, apparently, it seems that I have done this presentation during the night, because I'm going to do exactly this. I've first had some fun in playing with artificial intelligence. I asked ChatGPT what the technology was, and actually he provided me with at least 7 possibilities, from measurements of the electrochemical potential, measurement of the protection current, visual verification, visual test, polarization measurement, analysis of the chemical composition of the soil and the water, and so on and so forth. This is what ChatGPT is telling us. We will eventually choose one, and I chose the visual verification, so the visual test, basically. I was faced with 4 different types of corrosion. I've been doing cathodic protection for 33 years, and I managed 12,000 kilometers for the Hera group, for In Rete, and so I had some cases to choose from. And therefore, I chose visual inspection on the earthed elements, earthed networks. So what can one find during an inspection? With a visual inspection, let's assume that I do an excavation, that I dig, and I find this kind of tube, and I detect a gas leakage. Actually, what you see here was just a rapid intervention to fix the problem, but so we will face 4 different cases. I took a picture and I asked the artificial intelligence to ask what type of corrosion was. Actually, the system replied with a given answer. In some cases, she was right, artificial intelligence was right. In other cases, it was not able to give the right interpretation. Our case study will be the tube that has not been corroded. So we have at least the electrochemical potential and protection currents. Now let's have a look at the cases. And the objective of the survey I would like to involve you in is to identify in each of case some value potentials in the 24 hours. We will try and associate the 2 potential values, and we will then choose the potential which, in your view, might be correct. First case. So this is a pipe of 1985, which was no longer used in 2024. That's in steel, medium pressure network, earthed laying, impressed current in a system of cathodic protection with no interferences. So I took this picture and I interrogated ChatGPT, and that told me that basically it is localized corrosion. It's evident that the metal was pierced, and this is basically the information given by artificial intelligence. I'm sorry, the speaker. So this is a case in which the potential value is protected. In the other case, there is no adequate protection or lack of protection. And basically, the survey foresaw the choice of 1 or 2, but this was already said, but there's some information missing. So this was the case. This means that this type of corrosion, this type of protection is telling us, the graph is telling us that the situation has always been like that. The protection was there since 1985, and the coating was damaged to such an extent that current was not capable of providing the effective protection.
Caso B.
Then second case, B case. That was laid in 1991. The pipe was no longer used in 2007. The type of cathodic protection is always the one we had before, and there were interferences. Here too, sending the picture to artificial intelligence, this is what we get from the artificial intelligence system. We have corrosion by pitting. We may have a potential where you have interferences, as in case 1. In case 2, there are interferences, but less. In the first case, there are even anodic situations as well as cathodic situations, while here we are in a case in which, in spite of the fact that there is this type of corrosion, here I still have corrosion in spite of the many variables. So this is a something that is linked to the lack of coating or the damaging of the coating itself. Third case, this pipe was laid in 2003 and no longer used in 2008. There too there was a variability because of interferences, and as a matter of fact this is a type of corrosion because of stray currents. From the image, the artificial intelligence was not capable of saying that it was corrosion from stray currents, and therefore I interrogated the artificial intelligence once again, asking if it knew what stray currents were, and so on. And in this case here we have our two potentials with two anodic spectra. In the first case, we have the protection criterion -85, and here we even have ineffective protection because the pipe is telling us that that was used in an environment in which there were lots of interferences. It was left there for many years, and when it was then used again after some time, we found the leakage. So that was the problem. So the pipe was never placed in protected conditions. So this means that there too we're not getting any benefits to our pipes.
Look at the videos. There was a survey, there was voting, quite a lot of things.
Anche prima probabilmente non ero molto chiaro nemmeno io in quello che stavo presentando perché
I was not very clear when I was presenting before because that was not the right presentation. So if you look at the potential trend, this is a record done in 2023 before the pipe was stopped being used. So you see the protection value here. We're talking about 25,100 seconds. That is not compliant. And apart from applying cathodic protection with impressed current, some non-stationary interference occurred, not right away, but some time later. So we did some mitigation activities, and then we will see that there are corrosions, zero corrosions. This pipe in the last 10 years, that is the time we have available, was never subject to corrosion. So corrosion zero. There was never gas leakage. And so later on we will try and find some justification to this. by reading the standard. For example, since 1981, when I protected the pipeline, to 2008, when the non-stationary interference occurred, here you see we have the TFL values, 50,000, 60,000, 43,000, from 2012 to 2023. From 2009 to 2012, it was never compliant with protection criteria throughout the year. So the system was always in such conditions that would not guarantee conformity. And here you see the situation every day. Even more, 80,000 seconds per day. In 2023, the situation was a bit more calm, but always over 20,000 seconds. This is to show that nothing should be taken for granted. In the year since 2008, this pipeline has always had potential values that were not compliant with the standards. Here you see what we saw before. It's a Zonda potential graph. In 2021 or 22, we placed the probe. The last record was obtained in 2024. This is just to say that we could have done something to mitigate this non-stationary interference. And let's have a look at the situations, at things that were done before the probe, AS, BS, and so on. Before the probe, we would analyze the efficiency of the supply unit that had a constant potential, and the graph shows a discretely constant. And here you see the variation of the current from 6 amperes to 12 amperes. And the current is in situations in which you have anodic peaks and you have more cathodic peaks, and so supply goes down. And again, looking at the situation in the past, my supply power unit worked perfectly with the constant potential. It's important to compare the current supplied by the supply unit and the cathode potential. What I'm trying to say is that the first graph refers to the cathode potential compared to the graph of a current provided by the power supply unit. In all these circumstances, like here, for example, where I have 6 amperes here, so when there is a reduction in current on constant potential, I have entering current on the pipe. So I have a cathodic current in this condition. And here I have minus 1.5, so the potential value is cathodic. In this case, I have a positive value on the top. The same when I'm in an anodic condition with the impressed current plant, where I provide more than 10 amperes. In this case, my anodic condition leads the potential to a more electropositive value. And all trends are the same, are going in the same way. When I'm in an anodic condition in the power supply, I have an anodic condition also in the remote point. So what can I do with the mitigation of interference before the probes? What did I do? Well, I would go there, increase the current value to reduce the number of seconds. So an increase in power, in current supply. once the probe were being used, in the last few years, we've been able to do this. So as a first step, I analyze the current on the coupon, the trend of the current on the coupon, versus the 𝐸 potential. And the graph of the 𝐸 current is like this. This is 0. Minus indicates situations in which I have anodic current and situations in which I have cathodic current. Over they are in cathodic, whereas under they are in the anodic current. What happens to the two graphs if we compare them? Every time I'm in anodic condition, the potential goes positive. In this case, I made the graph larger to have the opportunity of analyzing cathodic and anodic current. And as you see, the cathodic current leads to a potential value that's more electronegative. With the anodic current, the potential is more electropositive, and the trend is the same. As for step 2, I can do something more. I can analyze the coupon current graph, comparing it with the current, a graph of the current provided by the power supply. When we are in an anodic condition, also in this case, we will find the same situation. Let's analyze the graphs. We have the anodic current. When I'm anodic in terms of 𝐸 current, the supply is higher. So the highest supply is when I have anodic current. I hope you can follow me. So when I have cathodic current, the supply by the power supply unit is lower. And so I have cathodic interferences. And what does this mean? This means that mitigation, because our aim was to have an historical mitigation or a new kind of mitigation, mitigation of interference does not provide any success, because we're talking about 25,100 seconds outside protection. But corrosion equals to 0. So in the last 10 years, there were no leakages. So since 2008, this pipeline has potential that was at unacceptable values. So how can we explain this 0 corrosion? Well, I can offer my own interpretation. The 50162 rule that refers to stationary interference in attachment D, it refers to current probes to assess the interference of stray currents using this very simple scheme: one electrode with one probe. So current probes can be used to assess the variable interference due to stray currents. And attachment D also says, through this graph, that the trend of a current in the probe is like this. In this case, we have a 0 value, no current. And when you have it in cathodic current, it's going out in, whereas the anodic is going out. Period A is the one in green, is the period in which the pipe doesn't have any stray current, like at night time. So what they're telling me is that here, when there is no interference, generally your reference value is 100% of cathodic current. We can reduce this figure with anodic interference. But when the anodic is higher than the cathodic, there is corrosion. So this same graph also tells me that there is a B period. A B period is a period in which you have the highest anodic interference. So it identifies an hour in which you tell me that you have maximum reduction of current towards the probe. So you have more anodic situation. And then in a following table, we have criterion of the probe current. So if we look at the different percentages of current in the different periods, here it says what you are using this table talks about the current criterion, probe current criterion. So in this case, I emphasize 2 points. When I have a current value lower than 30%, like 29, the reference value is acceptable only for a cumulative time up to 72 seconds. On the 73rd second, corrosion starts. So if I'm at 30% of maximum of the reference value for 72 seconds, I can accept it. On the 73rd second, the situation is unacceptable. The same when you have anodic current, and so you can accept only 3.6 seconds. So if it's less than 0%, so it's only anodic, the acceptable seconds are 3.6. Okay? Corrosion risk occurs when the values of the probe current are lower than 100% and last longer than the time indicated in the table. But it's true that if I look at my previous graph of the current of the probe and start thinking about what we've just seen, I can identify a period A and period B. In period A, I have a percentage that I think is the reference value, that is 100%. And there are anodic and cathodic conditions, even though it is an entering current. I did an average, I calculated an average. But then if I check, if I look at percentages here compared to the average value, 20 microampere, and I check what happens inside during period B, where I have the more anodic value of the current, if I do some additions, and I check the only anodic from the 4th second afterwards, in an hour I have 330 seconds, and if I'm just 1%, is 420 seconds in an hour. If I multiply by 10, because I think that for a couple of hours at night nothing will happen, and I have about 4,000 seconds that are not admissible. 4,000 seconds if we do an assessment of a potential value that is 25,100, this clearly shows that corrosion is present. There's no doubt about that. Corrosion due to interference. But with the 4,000 seconds, we could see things differently. But facts are there. Case D shows no corrosion. So to conclude, because of course I have doubts myself, and so it will take time to apply this kind of idea. Zero corrosion is justified through the probe current. Today, efficacy is defined by the value with plus or minus the ohmic drop of the potential. We cannot measure the effectiveness through the potential. That is all from me, and thank you for your attention.
Grazie Lorenzo, che è riuscito.
Thank you very much, Lorenzo. He finally managed to show us the animations in his presentation. And also thanks to our people here in Automa who managed to solve the problem. Let's now move the floor to another speaker. Let's keep the questions for afterwards. I'm sure there will be many of them. Okay, now I would like to welcome Alessandro Matteo Longhi to 𝐲𝐻. He's not alone. At least he shouldn't be alone. We also have Massimo Grigis. Comparative tests of electrodes. So maybe we can understand a bit of what we should use.
Non sono molto avversa a queste presentazioni, quindi siate clementi. Ok, si sente? Perfetto. Quindi avete già visto che partiamo male.
So this work follows the previous work that we presented last year. I don't know whether you were here last year.
Il titolo della presentazione è abbastanza chiaro, no?
So we decided to compare in the field some electrodes with coupons. So with the leak simulator. The activity was carried out by myself as a representative of 𝐸 and Massimo Grigis from 𝐸𝐴C. My colleague already presented 𝐸. It's a second national distributor. And 𝐸𝐴C is a company that is specialized in the field of cathodic protection. So last year we presented the first part of a study with certain test fields. Today we have created 15 test sites with 60 electrodes with coupon in 8 different types of electrode. And today we're going to see the results. Why did we do this? This morning we talked about artificial intelligence and so on. But we looked at everything that is above ground, machines, artificial intelligence, but what do these machines interpret and assess? Well, what they read is the potential of the pipe or So everything that is above ground already has been studied in many different ways. Everything that is underground, especially with the coupon, has not been studied very much. So we said, should we update our systems? Should we place thousands of these coupons by a certain date according to law? Yes. So as a company representative, I will have to go and ask for money. I will have to carry out different activities. And then if we don't get enough, I don't get good results, I won't work anymore. So I wasn't really pleased with that. So the question was, what are we going to lay? So what kind of test did we do? We used real distribution plants, old plants with bitumen covering, with interference, plants between Milan and Varese in a highly inhabited area. The sites were divided into 3 categories. 1 to 5 are sites where these electro coupons have been placed with high resistivity backfill. And 6 to 10 with high resistivity backfill, and 1 to 15 backfill with low resistivity. 1 to 5 and 6 to 10 are the real conditions of the pipeline. 11 to 15 are a bit forced just to understand what happens when the backfill is different, when the conductivity, the resistivity is different. But then if you have a soil with high conductivity, then probably 11 to 15 is more suitable. Here you see the electrodes. We tried several of them. The backfill is visible. Here you see we have a bucket just to put the backfill in. So we would fill it in and then we would take the bucket out. We follow the same geometry for all of them, distancing and so on. Then if you, of course, I won't go too much into detail. If you have any question, you can ask me later. So we installed them in 15 sites. Here are some pictures. And here you see the first sites. You see the backfill that we used, resistivity, digging soil, 130, 182 in resistivity. These data are fundamental in order to better interpret the measurements that we calculate. The type of coupon, the type of electrodes, A, B, C, D are different brands. So here you see the coupons that we used. I will skip some parts, but I will give you a copy of the presentation. We checked that the different coupons did not cause any interference, so that our tests are not influenced by interference. So the distance between the different coupons, the different electrodes, make it safe, interference safe. But let's talk about the kind of measurements that we did. 𝐸𝐴 potentials. 𝐸-sonda is the name that we use. 𝐸 on coupon. Then 𝐸-OFF. That's called EPBT, the acronym. 𝐸-OFF measurements. Then we measured current on the plate, the natural potential of the depolarized and corrosion-free on the coupon, and then the on potential, how the ion potential with a coupon detached, disconnected. So mainly it's ion on plate. In the first part of our presentation, we were wondering what is the correct value of potential and what is the best electrode to satisfy my needs. So for my pipelines, what is the best device? That was the question we wanted to answer. However, this study led us to another question. What is the protection criterion to use? Because when we use coupons, the protection criterion is not something to be taken for granted. It's a complex choice. Let's have a look at the measurements. You will see different graphs with the 𝐸𝐴 and 𝐸 to check whether there is a difference. There shouldn't be. And then 𝐸𝐴 and 𝐸 minus 𝐸, so a potential drop. And then the natural free corrosion on these plates. And then 𝐸 and 𝐸PBT, depending on the current measured on the plate. So 𝐸 is always between plate and electrode. And then the last one was a measurement where I compared the different electrodes, but not on the plate, but on the pipe, to check what I'm observing. So I divided them by group, homogeneous group of soil or backfill. Here we have the 𝐸 on plate, then 𝐸, different sites, and the different measurements. Here I see that on side 5, these devices give me more or less the same 𝐸 value, but the 𝐸 shows some differences. These are figures, of course. Then we need to understand what they mean. Here you see the same kind of graph on sites number 6 and 10, where we used excavation material. We have the 𝐸, the E probe, and the 𝐸 in continuous over a plate. The device is constantly opening and collecting samples. And also in this case, we see some differences, significant differences. And in the last group of installations, we have the 𝐸 and the 𝐸PBT. In this case, there are significant differences in both cases, for 𝐸 and for 𝐸PBT. So depending on the device that I use, there are differences. This is the second group of graphs, where we have the 𝐸, the E probe, and then 𝐸 minus 𝐸, so the drop, the voltage drop that I expect to see. So in this case, the drop is not trivial, it's not negligible. It's quite significant. And then 6 to 10, the situation is the same. The drop is significant. And we're talking about -1 values, not values in which I expect a significant drop. So also with protection values, the drop is significant. The last groups of sites, 11 to 15. Here, in some cases, these lines are not growing very much. So in this case, also for ion values that are negative, the drop is not significant. But there is a drop nonetheless. So we cannot say that by placing a probe, I have no variation. I have it also with potentials that are not so electronegative, so I need to be careful. But then we said, where should we start from? Why do I have these differences? What kind of plates are we using? In this case, we decided to disconnect the plates and measure free corrosion. The same site where we have 4 devices, we disconnected the plates and checked how they depolarize. We checked the different ion potentials. We saw it before. Let's see how they behave. This is after 1 day, and this is after 1 week. We can see the potential differences in natural potentials are significant. 200 millivolts. So depending on the site, the natural potential of plates can vary significantly. And we need to bear this in mind. This is an important figure, resistivity and natural values. The same happens in the other sites. They're not always the same, so there is no fixed rule saying this equals that. We found some trends, but they were not always confirmed. So each site has a different figure. It's important to know that the natural situation of the different plates are different. I have, of course, tried to give an interpretation, but I'm not sure it's the right one. This is another graph. Here we have the current that we measured on the plate and the potential. We have the ion potential and the EPBT potential. Here you can see that the ion potential follows a trend where we see that it keeps a bit of resistance. So it's better to have a plate. But the linear trend is there. There is resistance. As for EOF and EPBT, we can see that at a certain point the oxygen consumption is saturated, so potential will not move very much. This is -1. Here is 0.85. Then maybe with lower potentials, the situation is different. But this is something that we've always thought. Managing a -1 is okay, but if I have to manage this figure, am I protected? I may have doubts on that. Here you see the measurement of each electrode, the ion between the electrode and the pipe. Here you see that they're almost identical. Electrodes are probably seeing an equivalent failure or leak. Here you see that during the lay of the products we made mistakes, and you can see very clearly that these measurements are wrong. In some sites, we were not able to create graphs for this product because we made mistakes when laying the product. Are the graphs clear enough? Because that's the important point. And here you see, they see the same leak. In this case, potential here is much more negative. The more the closer I get by measuring the plate, then potential got closer. So things are logical. We have entry current in the pipe. So yes, in the past values were different, but these ones are purer than these values that are a bit exaggerated because of the drop. But we strive for perfection, of course, so we need to continue along this path. So 𝐸 gave us different values in the first analysis. So the doubt was, what am I measuring exactly? Is it a clean value? Well, not really. There is a bit of drop. I was surprised to learn that EPBT, 𝐸, was different in different sites. But I thought that once the drop was no longer a problem, the value would be the same, but they are not. So this value that I would generally use to assess the effectiveness of my cathodic protection, in the same site, depending on the product, I can find differences. And it's also true that in some cases, some products proved to be extremely valid in certain conditions. All of them had problems with residual drop. But there are products and situations in which figures are good. This is what we understood by looking at those graphs. So my question remained the same. Which is the right value, the right criterion? So the coupon shape, no, it didn't really influence in a significant way the values. Size of the coupon, well, as long as they are similar, 10, 12, 15, it's okay. 35, of course, it may have an impact because the leak is bigger, so it needs more current to polarize. But once you decide the type of leak you may find on your pipelines, it's okay. The real difference is in where the coupon is with regard to the electrode body and laying depth. If there's 60 centimeters of difference between one probe to the other, there is a difference. And the climate plays a role. So measurements are okay, but they have different meanings depending on where the coupon is. Some coupons are more shielded by the electrode, others are more exposed to oxygenation. So oxygen diffusion influences the natural value of the plate. And then the best performance was clear in some cases. So this potential, so soil resistivity and free corrosion potential are two parameters that will play a role in our assessments, in my opinion. And then, of course, I'm willing to answer to any question that you may have on the subject. So based on what we said, we tested 15 sites, 60 devices. We used up a lot of time. We had fun. But but my fear is that when this approach has to be applied to 20,000 measuring points by remote control, I'm a bit scared. I will need to find standards and they have to be as clear as possible so that I can interpret my measurement based on those standards. But the most difficult part will be the application of these methods to very large methods with a lot of measurement points. We have a technical staff, of course, but I'm a bit uncertain when it comes to such big sizes. Let's move on to the second part. I do my measurement and I read my potential minus 0.85. I'm okay, I'm protected, everything is okay. I'm not interested in the type of coupon that I used, where I placed it. I reach minus 0.85, I'm okay for 24 hours. But what if I don't reach this 0.85? With the EPBT that we checked, they were all around minus 0.8, 75. This 85 is not so easy to achieve. In some cases, it's almost impossible. So it's very important to consider what we do in case I can't reach that threshold. The law says that soil resistivity and the free corrosion potential, those two elements allow you to understand the kind of threshold, whether you can change it or not, because the standard allows you to change this threshold, increasing it. Here you see the standard. Depending on resistivity, there is the possibility, and also free corrosion potential, I can vary my threshold. We're talking about IR-free situation. 0.85 in our cases, with an ion potential of minus 2, 3, or 5, well, if we check purified potential, 0.85 is not so easy to achieve. Okay, so use resistivity, free corrosion. Well, but resistivity is not so easy to obtain as a figure. What should I measure? Because in a field, okay, I analyze 2-3 square meters of land. But in a city, everything is different. 10 meters, things can change very easily. So it's not so easy to have a very precise mapping. Free corrosion for protected plants requires quite some time. It took us about a week. So, okay, it's protected, I switch it off, I wait for 8 days, and then I have 8 days of non-conformity. So if you don't reach a 0.85, you can move the threshold if you have certain figures and data. And some technical expert needs to assess them. And then the standard says that in case you cannot achieve the minus 0.85, you could use the 100 millivolt shift criteria. But it's important that there is no interference on your pipe. In this study, we tried to show that the 100 millivolt shift criterion can be applied also in case of an interference. This is a bit of a provocation. I take some sites. Here you see a number of sites. Low variability. Then I check. Here is high and here is low. The E is average. The 85 threshold. I see that this one is not compliant. because it's minus 70 and some values are over 300 per day. So this measurement is not compliant. But the EPBT on which I want to apply the 100 millivolt shift has a low variability. What does that mean? This situation, where I have an E-probe, maximum and minimum, high variability, and this is the EPBT, the daily 𝐸. There is some variation, but it is low. I have 70 million between the maximum and the minimum. And then this site has certain resistivity, so I could reduce the threshold to minus 75. But even with minus 75, with an average value of 70, if I increase the threshold, this does not guarantee protection. So I was using that one, but is it interfered? No. It's okay. Let's try and apply it. Okay, I have here, I have a 300 millivolt delta. 300 millivolt is quite stable, and it's far more than 70 millivolt. Do I have a good perception of the idea that that measurement is not really concerning? Yes. Also because every 100 millivolts increase in the protection potential, I slow down corrosion. So this measurement complies, in my opinion. After doing all of these tests, I realized I had forgotten something. Checking the initial graph, in that specific point, I had resistivity that would allow me to have 0.75 as a threshold. But there was a free corrosion potential that was minus 0.22. Let's try and go back. So it was something in between this resistivity situation and this free corrosion situation, between 75 and minus 0.65. So 0.70 could be doable. And by using 70, it would have been compliant. This idea, in our opinion, is to be considered. For those of you who use probes, you will find these problems. When the values are purified, they are not too far from protection values. So a 0.80 is not so easy to achieve. Generally, you have minus 1, minus 1.1, minus 1.2. So understanding which kind of probe to use is a very important process, especially when we have to choose the type of probe. Do I use the backfill or not? If I do, I need the resistivity value because that value could turn out to be useful in the future. Another provocation by Massimo Grigi is the following. If you look at the laws, at the standards, you see that depending on the free corrosion potential, there is a corrosion delta, 400 millivolt. This is another important point, because the law says if you have free corrosion up to a certain value, with 450 millivolt of gap, this is 400. The law tells you that the important part is the polarization that you obtain. So this is also an invitation for those who will take part in standardization committees. Polarization is very important. It can be extremely useful because with the new probes, the new protection values are not so easy to reach, the apparent protection values, because in my opinion, that point is totally protected. Obviously, if in this case I had had a 300 millivolt variation and a 300 millivolt shift, then things would have been different. I had to check the records, check these statistical parameters, and in that case, it could be done. In some cases, the shift is not so significant, and so then it's different. It's not enough to have low variability on the EPBT. You need to check on the drop.
Sì, ho cercato di andare veloce.
I tried to go as fast as possible, and my presentation was not modified, so I knew it very well. Thank you.
Grazie della presentazione che di sicuro ha...
Thank you very much for this presentation. Look at the last contribution. So I'd like to ask Luca Casanova from 𝐸𝐴, who's going to talk about the verification of passivity conditions of carbon steel with cathodic protection with in situ techniques. Thank you very much, Marco, and thanks to the organizers. I really hope I won't leave you with a headache. My presentation is a bit more academic. I'm going to talk about some techniques mainly used in the lab, but I think these lab tests have provided practical and interesting results also for on-site use. My background is more academic, more of an academic type. I worked with Marco. And during the site, I think the questions were asked are quite simple. As often happens in the scientific world, if you pose scientific simple questions, the aftermath is a bit more complex to answer these questions. So we wondered, first of all, what's the state of our steel when it is protected, when it's covered maybe by an oxide. And another question was, so this metal in polarized conditions with a high degree of alkalinity on the survey, how does this change? How does its state change? To answer these questions, we started the system. So we polarized iron steel, pH 13, and I'll tell you why we opted for this, why we started with an alkaline pH. We did a test of an electrochemical cell, slightly different condition compared to that of an acid pipe. 60 hours test, which is quite a limited duration. However, for an experimental setup, that's quite prohibitive because the test was run also during the night with no surveillance and all related risks. So in order to understand what's the state of a metal on nanoscopic scale, one should use peculiar instruments. So you need to know how the surface is made up of it. So you need to use the atomic force microscope. It's like the tip of a record player, and the rugosity, the ruvidity profile enables us to have results. And then you have laser. The laser is basically directed towards the steel, and the laser, the return beam is analyzed through a Raman spectrometer that tells us a lot in terms of what kind of substances developed. Like I said, we worked with pH 13, and the reason why was that the surface with this kind of pH value remains clean, so it does not get dirty with corrosion products that might disturb the analysis. And then the pH 13 made it possible for us to analyze if at -1.1 we could have a higher pH compared to pH 13. In literature, there's lots of data There's lots who actually talk about pH 10 or 11. Others even say pH, even use pH 14. The natural potential is high resistivity potential. So that's for soils with the resistivity higher than 1,000, so noble potentials. And after 168 hours, we can reach quite high values, minus 100 volts SSC, which is silver chloride. So the diagram is quite clear. So if we are in a condition of free corrosion, the natural potential is telling us that we have hematite. That's quite a protective kind of oxide, which protects our steel in quite a significant way. If we apply the potential of one unity, pH 13, we are at the very limit of the hydrogen development curve in the domain of magnetite, which is less protective than the previous one, and it catalyzes the oxygen reduction, which is the one that we use to protect our tube. This is an improvement we implemented to actually use these technologies as best as possible. Namely, we introduced nanostructures to have more signals from the Raman spectrometer. And these are the peaks that we analyzed that tell us what we have on our tube, on our pipe. As regards the electrochemical values we used, we worked as follows. We worked on the we applied two steps. 2.1 currents are quite high. They're very different compared to type with a triple layer. In this case, the situation is similar to that of an uncovered tube in water, in seawater. And after several stages of polarization, protection current goes up because it's more difficult to in a way, have good potentials for the steel. This brings about important modifications, which is due to the alkaline values that are developed on that steel. And these conditions will then play a significant role if there are some external conditions, like, for example, an interference in alternate current. These are the polarization resistances that get developed, and as you can see, the values are quite low. After a number of polarizations, the alkalinization process changes the oxides that are developed on our material. In particular, the oxides are made up by a number of stages, and these stages are less protective. So if there are defects on the coatings, we expect a spread resistance which is low, which is assumedly low. Therefore, it would be interesting to assess if there are high densities of alternate current. It would be interesting to analyze the upper limit to use for the continuous protection current so as not to have any corrosion. Through the electrochemical analysis, it is possible to have values, the values of thickness of these oxides, normally some tens of nanometers, and their thickness increases as time goes by. These are the stages that get developed on our material in conditions of free corrosion. We mainly have hematite and magnetite. So these are protective oxides. If we do cathodic polarization, the hematite gets reduced, and you only have magnetite, which is less protective. And you see that there is this peak going up. If there are future polarizations, protection currents increase, and this alkalinity has an important effect on the chemistry of the materials being formed. These correspond to these stages. So beyond a certain level, the magnetite is no longer stable, and you have these two elements, these two oxides, less protective than magnetite. So with excessive polarization, we have changed the materials that get developed on our steel. This is what I was talking about before. This is the topography. This is how our steel looks like at a nanometric level. After 200 seconds of polarization at -1.1, you can see that there is a variation in topography. So it takes really little for major changes to take place in the surface of a metal. If you move on, if you continue with the polarization, this alkalinization also brings about important effects on the surface. They also expand the specific area of our sample, and in turn, this means a larger quantity of current required. Here we basically used laser on these parts, and they correspond to deposits of hematite and magnetite. So the first question that we asked ourselves, in case of extreme polarization, steel is never bare, so to say. It's always covered by an oxide. And then the second question was, what is the role of this pH? What does the pH do? Beyond certain values, here we're probably closer to pH 14 rather than pH 13. So in these cases, we have a dissolution and and formation of crystals process. And this brings about an important result. So basically, the study enabled us to, first of all, understand that it might be useful to study some points in this diagram in this area. This was for Marco, so that he can have me carry out other experiments, basically. So the idea is to use this current density and see if we apply a quantity of current higher than 30 ampere per square meter, if we have corrosion or not. And then the second result, the second finding that we might derive from the study refers to the inspection of pipes. So there we could carry out assessment techniques mainly based on frequency signal, and then we detect the signal. And then the study basically showed what the materials are formed on a tube protected with this potential. And so you can use the values of magnetic permeability in the various stages to carry out more reliable quantitative estimates to see if a defect on a coating is active or passive, and actually what the most reliable corrosion level is. So I'm done. I was very, very brief. Thank you very much. Thank you very much for your kind presentation that was slightly more technical and more academic than usual. As with this presentation, we've come to an end for our presentations. For those of you who would like to remain here, we can open a Q&A session, and I have an immediate question to you. So you brought the samples to a very basic pH. Don't you think that this brings us away from the conditions of representativeness of what we normally have on the pipe? I mean, this is lab tests, this is lab data. How can we translate them on the field? What do we expect on the tube? What we expect to find on the tube is different conditions, and that's also due to the fact that the electrolyte we use in the field is more complex than the one we use in the lab. Then, it is equally true that even if the pH is very alkaline, cathodic reactions at the interface generate a higher pH, and that's shown by the following stages. So initially you start from very different conditions. However, with these current density values, we might even get to other values. Have you ever measured the pH of a tube in cathodic protection to see how basic it is when a defect is shown? I'm asking. I mean, I had some results here coming from the literature. Some of them refer to test labs, basically, even starting from neutral pH values. And the span is between 10 and 14. It is not that easy. Then just a few microns are enough to have significant variations. But actually other tests could be carried out and have more precise ideas on this. If there are no other questions for our speaker, I'd move on to the questions to the other speakers who presented in the afternoon. I'm sure that there are certain interesting questions for them. I certainly have some. So I don't know if you want to ask them as well. To Matteo and Massimo, there's one thing I'd like to ask. All the data we saw refer to off values with the off on the plate. So if I'm not mistaken, if we have an 𝐸-coupon or 𝐸-probe value, we have a residual that is highlighted by the 𝐸 off on the plate. You have an 𝐸 off on the plate, so there is some kind of residual ohmic fall on this. Do we have the same things if we have the 𝐸 off on the power supply? When the plate is detected, we eliminated the current, but not the current which is inside the pipe. In other words, there's still an electric field in the ground. Yes, that's true, but the plates adhere to the electrode. So when we detach the plate, we've seen that that plate does not suffer any, is not subject to any kind of interference. So when I detach that, that's not possible. When it is not still connected, it still has some oscillations, but when it is detached, there are no interferences. Have you carried out any comparison off on the plate and off on the installation? Not in these tests. Not in these tests. However, we are using SNAM's testing standards. And within this context, we're doing a lot of this comparison between the 𝐸 off on the plate and the 𝐸 off value, traditional 𝐸 off value from the power supply unit. And I can tell you that except for a few peculiar cases in which you have interfering currents, things can be easily overlapped. So this is something that is not of concern for me. So I'm not worried of the fact that I might add additional problems with the plate. Quite the opposite. I'm better and more positively impressed by an on-off on the plate. The on-off on the power supply, it does not return reliable data in my case. But I wanted to spend a couple of words because I didn't support my colleague before in the presentation. He was left alone. He did perfectly, so I'm not going to go over what he said because it was well explained, well described. However, there was somebody in the audience who said, well, I thought you were going to reassure me, but what you told me was, you left me with lots of confusion. These were the comments made from the floor. I think this is quite logical and normal. We are still investigating these aspects, studying them, so problems like this are normal. I'm not going to... my intention is not to, in a way, trivialize the data given by Alessandro, but maybe give you some more reassurances. Alessandro first posed the problem. Cathodic protection outside of the ground and in the ground. This morning I listened to Ivano's presentation. I will be a prototype of this machine as well, and I will start working on it. I'm very thrilled of the fact that I can, in a way, do all sorts of plays to come out with interesting results. And actually, that he was talking about tests outside of the Earth. My colleague was talking about the 𝐸𝐻 experiments. Actually, Alessandro oftentimes continued telling me we need to write that each and every time the technician will have to choose the probe and decide what's the most appropriate probe is for his soil or his peculiar situation. And actually I continued replying, you just go to an audience and you tell them that you have to choose the probe wherever you are. That's crazy. The synthesis here is, in my opinion, the following. We have a device to be used outside of the Earth that provided for a very interesting upgrade. We have someone who reported about very interesting things, but these problems, you can start identifying the rationale and the logic. So if you have an expert and a physicist who's there, that is difficult to manage. But if you bring this data in a software, to a software, that can be managed, and that's our ultimate goal. Then everybody's done very complicated things, and I'd like to bring you a very practical example. This morning, 𝐸𝐽𝐻 said lots of interesting things, but I did not agree with him on many things. That's normal. He said, okay, I can do my on-off measurement and I keep everything regulated at 0.85. I can already save a lot of ampere. Well, wonderful. As a technician, I don't want to go to the same place to adjust, so I keep everything at a higher value, while if you can regulate day by day, you can definitely save a lot of current. However, at the same time, I do not agree with the fact that you set 0.85 because I would like us to forget that value. That's an old parameter. We pretended that we used it. We were always told that there was an off parameter, and we always used it as a non-parameter, so we kind of didn't use it properly. And now we want to do serious regulation on the off parameter. We should go and read the norm, the standard, and not 0.85. The standard actually provides for different values, and 0.85 is just one of them. In all installations, out of all installations I know in Italy, we have graphs. My old power supply units, the old ones, went down during the summer and then they would go up. And actually, we would always say, don't worry, because if it is September, the value will go up again. So this was this statement of ours. Was this decision stupid or not? I'm not going to answer this question. What I say is that this reduction, if you read the norms, if you look at the table that Alessandro showed, that's also very interesting. That indicates the resistivity values, and you have to compare them with the threshold. Then there's also a second table which talks about natural indicative values. I would like to remove the adjective indicative, but fact is that revisions can even be revised in turn. And so maybe scholars, experts might convert those indicatives as natural potentials. If we make this mental passage between what's indicative and what's a natural real value, that means that we will have created a homemade shift, which means the following. We talked about shifts because we had read that on the NACE document. Americans invented the shift, but that's not true, because if you read our EN standard, that already contained a shift. We didn't said this explicitly, but that was already there. So my answer is that summer reduction is fine. And 𝐸𝐽𝐻, who will use algorithms and artificial intelligence, you will have to rationalize this, both in the software and in the revision of the norms that we will have to bring forward. I think that's important. I just wanted to have this consideration to comment what my colleague said. Well, I confirm what you said. One of the things that we saw was that in the immediate terms, and when I start just applying that adjustment, I have a very significant drop in current. So, for example, in April, when there is still certain humidity in the ground, and then in the summer, that current went up because it works on a constant of potential, and the natural potential, as soon as the soil becomes dry, that means that I am using a reference value which is more positive, so I need more current to go down. So what we can do with artificial intelligence is to recognize certain patterns, looking at the information available, and automatically even change the adequate threshold depending on the time of the year. If we want to reach enough potential of, let's say, 0.9, and to do that we have to give 3, 0.9, and 8 in the summer period, the value of the summer period is already too much for that structure. It would be enough for me to reach 0.08. Plus, one of the things that we saw is that we do not necessarily have to reach the most positive potential, because the balance is found on a value that can be even negative. But yes, definitely, with this possibility in mind, we can even work on artificial intelligence to modify the thresholds during various periods of the year. Grounds are very peculiar. Oftentimes, they're not homogeneous. So when you do the measurements, they're not homogeneous. So one tiny part on 1 square centimeters does make the difference. And plus, the soils, especially the sandy soils, have peculiarities. So if it rains 30 centimeters between the various coupons, even if the two are very close, you may have the difference. So there is an oscillation which is significant for 30 centimeters difference in soil. So as long as we worked with -2 or -1.8, no problem. But if the potentials start becoming -1 or -0.8, well, then in these cases, the 100 millivolts of potential that change, and they change because the same soil changes. Its mineral part is always the same, but the conductivity of the soil is, for example, influenced by water. So if you work in details, I think the situation is very, very complex. It's very complex to do this kind of reasonings. These kind of reasonings are very beautiful, but also complicated. I'd also like to invite on stage Lorenzo, because his presentations are always very fascinating. There is a level of expertise and innovation which is significant. He showed us pipes. Some of them are clearly pierced, perforated, and they were in a condition of protection which was compliant to the norm. And then there was another type, not corroded, but for most of its life, that was in a situation of a non-compliant protection. So this means that we might, for example, start thinking differently with reference to what's compliant and what's not compliant. If something is compliant, does that really mean that the pipe doesn't get corroded? And is the opposite, does the opposite apply? So my question is the following: compared to the measurement point that was used to do the measurements, were these damages close to one another? Were they far? How is our measurement point representative of the entire pipe? Well, case D had a measurement system with a probe, which was 2 meters from the part that I brought and I was brought here. So that was by chance, on the occasion of some works on the ground. And so I wondered actually what that could be due to. So I really wanted to have that sample to analyze it. And actually that sample surprised me. I would have never expected any type of corrosion. All 4 cases were covered in tar, in bitumen. For sample D, that's even visible. We even thought that there could be a significant detachment of the coating, because we were we were still making hypotheses. We were still making assumptions on the non-perfect adhesion of the tar. But actually that bitumen, that tar, used for the coating in 1981 was made better than the last ones that were applied in the years 2000. So after all these contributions, there's one thing I'd like to say. I'd like to say once upon a time. Once upon a time, there was an old criterion of 𝐸𝐸 talking about the criterion of the 100 millivolt shifts. That was then abandoned because interferences would go up and that criterion could no longer be considered valid. Today, however, we have lots of opportunities offered by the technological advances, artificial intelligence, and analysis underground or outside of the ground. In other words, we are moving from the search of the R3 as absolute value to the search of something new, for a new element of protection. So we're trying to opt for something that gives us a more precise indication that a type that we believe is protected is not in fact in that condition. What do you think? Yes, what you say is perfect. If you remember the graph that Alessandro showed, we had that depolarization. I'd like to say that from a technological point of view, this depolarization that was done before on the tubes, so we had to stop using the pipe. Those graphs were used by eliminating the protection of the plate, and we did that remotely. So today, there is the possibility of actually not protecting the plate and by assessing the polarization. Out of all the measurements that we talked about, to me, this is the most reliable one. Another thing that could be understood by if you look at the graphs carefully. But actually today we didn't want to talk about, establish some kind of a commercial discussion today. So you might have probably expected a question like, what's the difference between the various electrodes? I did find some differences. The electrodes are not all the same. The differences, if you manage to understand the graphs well, the differences were there. This was not the right occasion in which we could say that A is better than B. But we will certainly give a contribution so that these results on the differences between the various electrodes in the committee that is currently discussing how to assess the probes. But I tell you, there is a guideline currently being released, right? Yes. And plus, we have a document of the Polytechnic University that has to be made public. And inside that document, we will give our contribution to be able to differentiate between one probe and the other, because differences did emerge from our research. Other comments? Mine is a very short question. I've never dealt with corrosion and cathodic protection. In the next few years, we will have a backbone for hydrogen from Tunisia to the north, and then there will be local networks. So hydrogen will require different steels because it has different diffusion capacities compared to CH4. Are you ready for this, or will you need a lot of R&D activity to face this? I think that I can answer on this aspect because I'm participating in a lot of working groups on this as well. So hydrogen is a sub-product of cathodic protection. If we push it too much, if we do over-cathodic protection, over-protection, we go below 900 millivolts IR free, we produce hydrogen. So hydrogen has always been considered in terms of cathodic protection as a negative element that we want to avoid. We don't want it to be accumulated outside our pipes. The problem with hydrogen has not a lot to do with cathodic protection because it won't be inside the tube, but cathodic protection deals with the outside of the pipe. But what the contribution that we can give to cathodic protection is a series of effects that we've always analyzed of atomic hydrogen, which the effect made on metal matrices. I do not expect a drastic change in the materials of the pipes. The higher the damage in the material and the weaker it is, so it's much better to have a carbon steel that is softer than a highly resistant carbon steel for hydrogen. I don't know how much and the extent to which cathodic protection will be involved on this, but those who deal with networks like 𝐜𝐼 and the vast majority of the people present here, they will indeed be involved. Some things that see us involved for hydrogen refer to components. In other words, there are some components that are part of the cathodic protection system, for example, insulating joints, and they will be impacted by the blend and by the hydrogen concentration. They have components inside in elastomer, and therefore they will have to prepare components that will have to meet the new needs. Having said this, I would like to invite you to participate in our meeting on the 29th of November together with 𝐼𝐧, together with Alpha Engineering and 𝐜𝐼. We are organizing a meeting for the components on the components of pipes and the new challenges posed by hydrogen, and a whole series of indications will be given by verification bodies. So we will listen the experience of these people and the approaches and steps forward that are done by the market to meet this new challenge. So there is not a direct impact on cathodic protection, but on the components that are part of the system of protection, cathodic protection. 29th of November, Modena, Alpha Engineering with 𝐼𝐧. Don't know if there are any other questions or comments. If there are no other questions, I would like to thank you all very much for your participation. I think that we can declare our meeting finished. I would like to wish you a safe trip home in spite of the bad weather. Thank you very much.
Un saluto dal nostro ospite.
Grazie a tutti.
Thank you very much also on the organizer. I would like to greet you on behalf of 𝐜𝐼. Once again, I would like to thank you in spite of this bad weather, but many people attended the seminar today. Once again, we would like to invite you to participate in the Smart Grid Days next year, and hopefully we will have the sun shining. Thank you very much and enjoy your safe trip home.